Recording in progress.
Okay. We started our discussion on the isotopes, right? What are isotopes and what are unstable isotopes, what are stable isotopes? Can you recall the
Yeah.
difference between stable and unstable isotopes?
Uh, Stable
Mm-hmm.
isotopes are what's it
Mm-hmm.
called? How do I say it? Like they have what's it called? They have like the they have like the same,
Their nucleus is stable. Basically, their nucleus is
yeah,
stable.
non radio,
Yeah,
yeah,
yeah, they are
radioactive,
not radioactive. They don't emit
yeah,
radiation. Simply, we say that they are stable in terms like when we discuss
of
stability, we
radiation.
discuss we discuss stability in different definitions with different terms. We use different terms for
Yeah.
stability. Over here, for isotopes, we are on the basis of nucleus. We decide whether an isotope will be a stable isotope or whether it will be an unstable isotope. Okay, if any isotope is radioactive, it means that isotope is unstable because it is emitting radiations. Okay, it is emitting radiation. And if any
Mhm.
isotope is a stable one, then it means that isotope will not emit any of the radiations from it. Okay, its nucleus will be
Yeah.
stabilized. Clear?
Mm.
And can you
Yeah.
recall what is the application of radioisotope? One of the most important application
Uh,
we
like
have
that's
discussed.
like the most important thing in isotopes.
Application of isotope, radioisotope.
Uh, I'm not sure.
This it is written over here. We have discussed it. Uranium 235 in power stations. You remember?
Oh yeah, yeah.
What is it?
It's like different types of stations to make what's it called? Like make that generates electricity and
How they generate
gives
electricity?
out energy as well
How basically how
through the
isotopes are helping them?
turbine.
My question is that how the radioisotope is helping in power generation.
Maybe because they release like what's it called?
I told you that
Uh,
there is neutron bombardment on uranium. Like this is uranium.
yeah,
If you see this is uranium, and over it, if a neutron is bombarded, what will happen? This uranium will split into two lighter elements, right? As well as it
yeah,
will release what? It will release three neutrons. Okay, it will release three neutrons. These three
yeah,
neutrons will what they will do? They will further each one will further attack on uranium. Okay, on uranium
yeah,
again. Similarly, this will be split into two smaller lighter elements, and as well as it will release three neutrons. Okay, so what we have
yeah,
discussed that in this whole process, this is known as fission reaction. Okay, fission reaction. In such type of
yeah,
reaction, we have discussed that when neutron bombards on uranium, this is uranium, this is uranium, this is uranium, this is neutron, 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 neutron. What happens is that there is emission of lighter elements as well as there is emission of neutrons along with high amount of energy. Okay, over here high amount of energy is released, right?
yeah,
That energy is
yes,
used by power station. Okay, the energy
hmm,
which is being released in this process is used by the power station. How these power stations use this energy? Basically, this energy help to boil water. Okay, this energy help to boil water. Okay, and when water
yeah,
boils, it converts into steam, and from the steam turbines are run. Okay, turbines are run, and then electricity is being produced. Okay, so this is the application
yeah,
of radioisotope. That on bombardment of a neutron upon a radioisotope, just like uranium, there is emission of lighter elements as well as there is emission of neutrons along with a high amount of energy, right? This high amount of energy, which is being released from the uranium, is used for what purpose? To boil water and to convert this boiling water into steam. Okay, and then this steam is
hmm,
used to run the turbine. Okay, then turbine will run, and then
Yeah.
the turbine will produce
Energy,
electricity. Okay,
electricity.
from the
Energy.
water turbine, yeah, it will produce electricity in the power stations. Okay, this is the whole concept. I hope you are clear with this. Are you clear with this?
Yeah.
What is the application of radioisotope?
Yes.
Now, can you recall this? What is the
Like
application of this? Hmm?
uh, what's it called? The nuclear what's it called? Like the turbine gets electricity from the uranium and it breaks into parts, and then the energy is like spreaded into different radiations or
Hmm.
radiations that, uh, that will be used to give electricity, and then when you boil the water it creates steam from it, and
Hmm.
when the steam is created the turbine will move and it will generate
Electricity.
electricity.
Yes. Basically,
Yeah.
the bombardment of neutron on uranium releases a high amount of energy. That energy is
Yeah.
being used by these power stations. Okay, the engineers or the scientists who are working on these power stations, their work is to maximize, to use this maximum energy, to convert this maximum energy to boil water. Okay, for boiling water, like to make it
Mm.
as much as productive they can. Okay, their job is to check how this energy can be used for boiling water to convert it into steam, how they can utilize this energy, and how they can make it more productive, the system more productive, okay, by utilizing the
Mm.
energy. Clear?
Yeah.
Okay. Then we discussed about the what we can say about how we can write different elements, like how we can uh, like the oxygen, the isotopes of oxygen, they are oxygen 16, 17, and 18. What is same in these? Which thing is same? Hmm?
Like
If you see oxygen, yes,
yeah, oxygen. Yeah. What's it
which
called?
which thing
The
is same?
electrons and proton.
Yeah, electrons and protons. And what is different?
The what's it called? Neutrons.
Yeah, neutrons are different, and that is why we
Yes.
say which thing is same. Atomic number is same, or mass number is same
The
in isotopes.
mass numbers.
Think about it again. The mass number is same
No,
in the isotope.
atomic. Sorry.
Yeah, mass number is different. Why mass number is different? Why isotopes have different mass numbers?
Because of the neutrons.
Yes, exactly. And can you recall which property of the isotopes are same? Chemical or physical? Which property is same in all the isotopes of one type?
Um, yeah,
Mm-hmm.
what's it
Think
called?
about it.
Physical.
There are two
Uh,
properties, like we discussed, physical properties and chemical
yeah,
properties. I am
uh,
asking you which property is same among all the isotopes of one atom, of one element. Like if we talk about oxygen, we have three isotopes of oxygen, 16, 17, and 18. My question is that which property will be same in all these three
chemical
isotopes?
chemical
Yes.
properties are same
Why?
because of the electrons.
Yes. And why?
Electrons,
What is the function of electrons? Why we are talking about the electrons?
like the shells and
Hmm.
so how much electrons there will be in the what's it called isotopes.
The electrons,
It's
electrons
always
are
the same.
same, right? Electrons are always same. And what information does these
Yeah.
electrons give us? Hmm.
How many protons are
Ba-
there as well?
no,
Oh,
basically
also like the
we
chemical,
see
what's it called?
electronic
Mm,
electronic configuration, right? We write the
configuration.
electronic
Yeah.
configuration. Then in the electronic configuration,
Yeah.
we check the valence shell, right? We check the valence shell electrons.
Yes.
Then we check whether that element is going to, the atom of that element is going to share electrons or gain electrons or lose electrons. It depends on the valence
Yeah.
shell electrons, okay? So electrons give us
Yeah.
information about the bonding pattern, okay? The number of electrons. If I ask you what information we get from the electrons, your answer should be that the number of electrons, from the number of electrons we have electronic configuration, we have there are different shells in which these electrons are revolving. Okay, and when we write the electronic configuration, we always take valence shell electrons. Those electrons give us
Yeah.
idea about whether that element is going to share electron, or whether it is going to accept electron, or whether it is going to lose electron. Okay, this information we get from the valence shell electron. Clear?
Yeah.
Okay. Then are you clear with this? And that is why we say
Yeah.
how this electronic configuration help us to know about the chemical properties. How from this we are saying that the chemical properties are same. How
It
electronic
shows us like how
configuration.
much
Hmm.
like the valence shell electrons like shows us the bonding patterns.
Yeah, it shows the bonding pattern. I am asking on this, like I told you that about the electronic configuration. My question is that how this electronic configuration helps us to know that all of these have same chemical properties. What is the evidence
Mm,
from the electronic configuration?
the
See this
valence
way.
shell.
Yes, your answer. What will you answer? That the valence, since
The
all
valence
these three
shell.
isotopes, yeah, since all these three isotopes have same number of valence shell electrons. Okay, they have same
Yeah.
number of valence electron. That's why they will behave in a same manner. That's why their bonding pattern will be
Yeah.
same. That's why their chemical properties will be
Yes.
same. If you have 100 rupees and your two friends also have 100 rupees, okay, so you three will behave in the same manner. Okay, you three
Yeah.
will be on the same level. Similarly, we are discussing here, we are talking about the electrons in the valence shell. So, in all the isotopes of one kind, there will be equal number of valence shell electron in the isotopes, okay? Just like the carbon 12, 13 and 14. In all of these three, there will be 4 electrons in the valence shell. So it means they will behave in a similar pattern. Why they will behave in a similar pattern? Because in their valence shell, the electrons are same. Clear? Are you clear with this?
Yeah.
What about the physical properties? Why physical properties are different?
Physical because of the densities and the mass and yeah,
Hmm. Density. Firstly, we don't know about the
the
density. We
neutron
just
number.
say we know about, yeah. You will answer in terms of neutron number. You will say that the isotopes have different neutron numbers. That is why their masses are different. Okay, their masses are different, and that is why their physical properties are different. Their densities will be different. Their
Yeah.
melting point will be different, and their boiling point will also be different. The main thing is neutron number. Since all the isotopes have different neutron number, so their masses will be different from each other, right?
Yeah.
Okay. Yes. Then we have carbon 12 as our standard atom. Okay, you will see that at most of the time we will use carbon in organic chemistry. In the organic chemistry, you will check, or you will see that all the organic compounds, almost all the organic compounds have carbon. Carbon is the backbone. Why carbon 12 is so much? In carbon, we have three isotopes of carbon: carbon 12, carbon 13, and carbon 14. Now they are telling us why carbon 12 is much more important as compared to carbon 13 or carbon 14. Okay, why it is important? First thing I
Mhm.
told you, why we just talk about one isotope in the periodic table. Why we don't mention all the isotopes?
Um, Maybe because
Mm-hmm.
like the different
Like
because it has
I
like
told you,
different types of
there are three times. Okay, there are we they have different masses. Okay, then why we are not mentioning
yeah.
all the isotopes? My question is that why we don't mention all the isotopes in the periodic table?
Mm,
Hmm.
I'm not sure.
You told me this previously. You just forgot. What's that? Think about it.
Maybe because it has like different types of neutrons or electrons.
No, it depends on stability and abundance.
Or
Which one is more
uh,
abundant? Okay, like if
mm,
all the thousands of non-stable and stable isotopes are given the individual species, the first thing is if you there are many stable isotopes and there are many unstable isotopes, right? If we give
Yeah.
the space, if we make the block for each and every isotope, what will happen? The periodic table will become much more longer, right?
Yeah.
And it will become massive, and you cannot simply we cannot follow the trends. What are trends? Just like
Hmm.
I told you, what like we have trend in the groups that group number one will have one electron in the valence shell. Similarly, we have
Yeah.
trends in patterns. The pattern will change. Okay,
Mm.
the trend and the pattern will change, so it will become difficult. First thing is that. Second thing is, you know that there are. Wait a minute. Okay. I was also telling you about the on the basis of abundance. Okay, we check on the basis of abundance, and we always write those which are grouped in you can say the most abundant one. Okay, as well as we
Yeah.
check the that isotope property with the with all other elements of that particular period. Okay, for example, if I talk about the period
Mm.
number 4, can you recall how which elements are in period number 4? Group number 4, sorry, group number 4.
Oh. Uh.
Check from the periodic table and let me know.
Yeah. 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 There. Group number four. Yeah.
Mm-hmm.
So that would be like carbon. What's it called? Carbon, silicon, germanium,
Germanium,
tin,
yes,
yeah, lead, and fleurium, and
yes.
imperium,
Mm.
terbium, and
So all these
fermium.
they have some common properties in them. Okay. So why we put
Yeah.
carbon 12 here? Because carbon 12 is much more similar in properties with silicon and germanium. Okay. That is why we put this.
Okay.
So
But
we
I
have.
have a question.
Mhm.
Like for hydrogen, there is like the H symbol, but for Na, there is like a sodium, and K, there's potassium. Is there a reason behind these stuff?
What you are saying? Which symbol?
Like, hydrogen has the H, yeah, for
Mhm.
that's yeah, and for Na, there's sodium. It doesn't like make sense because there's no words between Na that makes sodium. Is there like a reason behind that?
Okay, yes, there is a reason. You know the what is the original name of sodium? Sodium original name is natrium, the Latin word. Basically, there are
Mm-hmm.
many elements which are from the Latin scientists discovered them. Okay, Latin or Greek scientists.
Mm-hmm.
So the its name is natrium. Okay, the sodium in the
Yeah.
Latin language, its name is natrium. That's why we write Na.
Mhm.
Okay.
Okay. Okay.
Similarly, lithium is Li, Mg is magnesium. You will see for mercury as well. You know, I can show you mercury. It is mercury. I think where it is. It is written like this. It does not make sense. Okay, mercury is written like this.
Yeah.
Why is it so? Because its name is hydragyrum. Okay, hydragyrum.
Mm-hmm.
So these are
Okay.
it depends on the original name and what they are using the alternative names. Okay. So hydrocarbon, it is also known as quicksilver. You know, mercury is also known as quicksilver. There are different names.
Mhm.
So we always write the names in the you can say we have name according to the Greek. Most of the names are written in the Greek language. Okay, they are not
Mhm.
written in their original language. Just like this. This is Hydra Gyrum. Although this is known as mercury. Okay, but there are some which have same name, same original. The same name is used there, just like H, hydrogen. Okay,
Yeah.
are you clear with this? Like there are
Yep.
selenium, bismuth, these all. Okay, then we have discussion about what I was telling you. Hmm. I was telling you about the carbon 12. Why we take carbon 12 as the standard? They have
Because it has like
mentioned.
different properties.
Hmm, what are some of
Like
the
super.
you know Some of the properties of carbon 12 are similar to the silicon, germanium, okay, the group 4 elements.
Yeah.
The properties are similar to the group 4 elements.
Yes.
So, can you hear me?
Yeah.
Yes. And secondly, first I told you that there is its properties are similar to the silicon, germanium, etc. As well as you know that they have mentioned, as you already know, an atom is so light that it cannot be measured in grams. This is obvious. We have discussed. You know, I told you like if in this dot, I place this dot. In this dot,
Yeah.
there will be around 2 million atoms. Okay, around 2 million atoms.
Yep.
So you can have idea now that how much smaller the size of atom will be, right? The size of atom
Yeah.
will be much more smaller.
Very
So
small.
you
Yeah.
cannot weigh it in grams. What you can do, we can the scientists came up with the idea that there should be atomic mass unit. Like atomic mass unit is like they can compare it. Just like for example, you have something and in one bag. Okay, you have something in one bag, but you don't know its weight. Okay, you don't know its weight. You want to know its weight.
Yeah.
What you will do? You already have something similar to it, and you know its weight. Its weight is 5 kg. So you will get the idea that it will also be 5 kg. Are you getting this? This is known as relation. We make the relative masses. These are known as relative masses. That one box, you don't know the exact mass of one box, but there is another box of any other thing, but and you know about that thing, you know the exact mass of that thing, so you can compare these two things and then you can deduce its mass. You know
Mm-hmm.
this idea. We use this
Yeah.
basically in different. So yeah, there is an idea about this. Scientists came up with this idea, and they think that they should introduce atomic mass units. So they choose the carbon 12 as the standard form. Okay, they choose carbon 12 as it is abundant and it is as well as what they did, they said that if we have any atom, okay, and we have carbon, and
Mm-hmm.
the mass of the carbon is 12, so it means it will also be
Yeah.
12. Okay, so this is
Okay.
how they relate it. Okay, if it is too small, if it is like this, so what they will do, they will compare it with the carbon 12 and then they will deduce its mass, like it will be 3 by 12 of the carbon, right, or 2 by 12 of the
Yeah.
carbon. Are you getting this idea? Like by
Yes.
comparing carbon 12, they got the answer. Okay, by comparing all the other atoms, basically it was not easy. It is not easy task. You have many elements. How many elements are there? 100 and 100. I think there was 116. What was the number? I forgot. 100, 118.
190, 108,
118. Yeah, there are
and
118 elements.
94 of them are of and the rest
Yes.
are synthesized.
Yes. So you cannot weigh their atoms. It is not possible. Atoms are too much small.
Yeah.
What you can do? You can have relative masses. Okay, relative atomic masses. For that you need a standard. Okay, always to relate something you must need a standard, and there is a standard that is what carbon 12. Carbon 12 is a standard, right? They have taken carbon 12.
Yep.
They choose the carbon 12 atom as the standard. They assign it to a mass of 12 unit. Okay, its mass is 12 unit. That means each of its nucleon had a mass of 1 unit. What does it mean? It means that if you got, for example, you have this one, this one. This is carbon 12. This is one atom of carbon 12. So it means you will give it one value. Okay, one. Similarly, this will also be given one value. Clear?
One.
Clear?
Yeah.
Similarly, if you have two like this, if you have two like carbon 12, so you will give 2 and the other one will also be 2. Clear? So this they have mentioned. They assigned to it a mass of 12 units. That means nucleon means the atom of it will have a mass of 1 unit. Are you clear? Like if you compare
Yes.
12 with 12, what you will get? 1, right? 1.
Yeah.
Okay. In other words, 1/12 of the total mass. Clear?
Yeah.
Are you clear with this idea? What they
Yes.
use? And it was actually a very good idea. This was easy, and this is in this way they related many other atoms. Okay. Then they use the
Yeah.
mass of nucleon to work out the mass of the other atoms. Okay. Then they use what? They use the
Yeah.
mass of the nucleon. Nucleon is what? Nucleon. What we say a nucleon is? What is a nucleon?
Nucleon is what's it called? Um
Mhm.
like something that gives the energy and
No, 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 no. What is
uh,
nucleon? Nucleon
no.
means the things which make up the nucleus. Which things make up nucleus?
Yeah. The what's it called?
What are present?
Uh,
Which two
proton,
species are present in
neutrons,
the nucleus?
electrons.
Hmm?
Protons, neutrons, electrons.
Electrons are electrons present in the nucleus?
No, no, only protons and neutrons.
Yeah, proton and neutron. So nucleon means proton and neutron. Clear? What they are
Yeah.
saying?
Yes.
Like if you have carbon 12, its nucleus will be what?
Like so that makes
Its
it
nucleus will be 1 by 12. Okay? Are you clear with this?
yeah.
This is what they are giving us
Yes.
idea. That if you have atom of carbon
Yeah.
12, its nucleus will be what? 1 by 12. Okay? Its nucleon will
One
be
by
1 by 12. And then by this idea, they check about the other nucleons of other atoms. Okay? They look, they took the mass of an electron as zero. Okay? This I told you already that electron mass is considered as zero. You remember the table?
Yeah, yeah.
This one. You see why now you see they have mentioned that the electron mass is taken as zero. You don't have to do anything with the electron mass. But why proton and neutron have one mass? This you already know by comparing it with carbon 12. Okay, you have carbon
Yeah.
12. Okay, the carbon 12 nucleus. If we talk about the carbon 12 nucleon, it will be 1 by 12. Clear?
Yes.
And that is why we give one mark to the proton and one number to the neutron. Clear? One atomic mass unit, one for the proton and one atomic mass unit for the neutron. Clear?
Neutron, yeah. Yeah.
Okay. Then we have, yeah. So the masses of all the atoms are relative to the carbon 12. This is very important. All the elements which are present in the periodic table, their masses, how they reduces the masses on the basis of the carbon 12. Okay, they related it with the carbon 12. Clear?
Carbon 12.
Yes. The relative atomic mass of an element, isotopes have different masses. So when working out the relative atomic mass for an element, you must take its isotopes into account, and average value is calculated. What they have mentioned now? Can you tell me this? What is this?
So like each isotopes have different masses, and to figure out like the mass, you have to find uh, the relative atomic mass for an element.
They have mentioned that isotopes have different masses, right? The isotopes have different masses.
Yeah.
So when
You have to
working
find
out
the
the
relative
relative,
atomic mass.
when you need
Yeah.
relative atomic mass, what you need, you must take each isotope. Like I told you, like for example, you have firstly you have carbon 12, right? So you will take its atom. Then you have carbon 13, you will take its atom. Okay. Then you have
Yeah.
carbon 14, you will take its atom. This is what they are saying. And then you will compare it with carbon 12, carbon 13 also compared with the carbon 12. We will always compare with
Yeah.
the carbon 12. But the atoms will be
Mhm.
different. Okay. Carbon 13 atom is
Yeah.
different, carbon 14 atom is different. Why it is different? Because their masses are different. Clear?
Yeah.
So it is
Yes.
not the case that if you are if you are comparing the masses, you cannot compare the masses of all the isotopes at the same time. You need to do this one by one. Okay, like for example,
Mhm.
if you want to know about the carbon, so you know that already carbon has three isotopes. Firstly, you will compare carbon 12 with carbon 12, right? Then you will compare carbon 13 with carbon 12. Then you will compare carbon 14 with carbon 12. Okay, because carbon 12 is the standard. We always have to compare with it. Okay. For
Mhm.
example, oxygen. We have oxygen 16, oxygen 17, oxygen 18. So
18,
oxygen
yeah.
15 will also be compared with carbon 12. This will also be compared with carbon 12. This will also be
Carbon
compared
12,
with carbon 12.
carbon
Okay.
12.
Yeah, this is what they have
Yeah.
mentioned. That isotopes have different masses. So when working out the relative atomic masses for an element, you must take its isotope into account and average value is calculated. Then you can calculate the average value. For example, how you can calculate the average value? For example, the its mass for oxygen it is 8.5 maybe. Okay, it is
Yeah.
8.7. It is 8.6. So you will take the average of these. You will add all these
Mhm.
8.5 plus 8.7 plus 8.6 and then divide it by 3. Clear? Can you hear me?
Yes.
Okay, sorry, there is an electricity issue. I just shifted my computer's Wi-Fi to the mobile data. Yeah. I was telling you this. Are you clear with this? How we calculate the average and all
Yes.
these things. Okay. And now I'm clearing this and let's see what they have mentioned. Now they have mentioned in the bold that the relative atomic mass of wait a minute, just 1 minute.
Oh,
Okay, now what they have mentioned over here that the relative atomic mass of an element is the average mass of its isotopes. Okay, average mass of its isotope compared to 1/12 of the mass of an atom of carbon. Okay, are you clear with this part? 1/12 of mass of the atom of
yeah.
carbon 12. This I told you that this is the
Yeah. So
mass of
like,
the nucleon, right? The nucleon of the
yeah,
carbon
nuclear.
12.
Yeah.
So you will compare the 1/12 of the carbon mass with the isotopes. Okay, for
Isotopes.
example, they have
Yeah.
mentioned how to calculate. This is very important concept, very important. They will ask you. This is a definite question which will come in your paper. How to calculate the atomic masses? Okay, how to calculate the atomic mass unit of anything? Like they have mentioned for
Mhm.
chlorine. So how you will mention for chlorine? Firstly, you must know there are two isotopes. You must know how many isotopes are there. So there are
Yeah.
two isotopes, chlorine 35 and chlorine 37. Chlorine 35 and chlorine
Yeah.
37. Okay, now they have mentioned 75% of atom in chlorine have a mass of 35 and 25% of mass of 37. What does it mean? It means they are telling us the ratio of the abundance. They are telling us
Hmm.
that the if you
Yeah.
will always okay when we have I told you just like in carbon we have carbon 12 in more abundance. Okay, always whenever
Yeah.
you have isotopes you will see there is a difference in their abundance. Okay, maybe one
Yeah.
isotope will be more abundant and the other one will be less abundant. Okay, so if you see here they have mentioned that 75% is making chlorine 35. It means this one is more abundant. Okay, this one is present
Yeah.
75% on the earth here
Yeah.
and this one is making 25%. Clear?
Mhm. Yeah.
And then yes, 75% into 35 plus 25% into 37. This is how you will do. You
There's
are you clear with this idea that 75% of the chlorine and 25% of this? Are you clear with this?
But why do you we use like 75% and 25%?
We need abundance. You know this they have mentioned above. This is the formula
Yeah.
to calculate the atomic mass unit. Wait a minute. Um,
But can't you use like 75% for like the first chlor?
Arohan, just wait for a minute.
Okay. Okay.
Okay, Rohan, after this meeting, I will share. Wait a minute.